Hello and welcome back to my channel. So today we're going to be talking about approximating functions with tangent lines. I believe this is also called local linearization. So we're going to be using tangent lines to kind of help us decide things about kind of other places in our functions. So things that we need to remind ourselves. Tangent lines are just a line. So when we are thinking about things with tangent lines, we need to remind ourselves that we are writing equations of a line. So we need a point and a slope. So everything boils back down to the equation of a line. A lot of this is just reminding us about linear equations and writing equations of tangent lines, but we kind of are going back to the idea of the equation of a line. Point slope form is realistically our easiest option, and our slope is that derivative. So let f of x equals 3e to the 2x plus 5, write the equation for the line tangent to f of x at x equals 0. So we're just writing the equation of a tangent line. So the things that we need to find is we need to find f of 0 to get our point, and f prime of 0 to get our slope. So if we start with f of 0, 3e to the 2 times 0 plus 5. 2 times 0 is 0. E to the 0 power is 1 plus 5. So we have 3 plus 5 to give us 8. So what I know is our coordinate point is 0, 8. Now we need to figure out our slope. So f prime of x is equal to, so we have 3e to the 2x times the derivative of 2x and plus 0. So this is realistically 6e to the 2x. If we plug in 0, 2 times 0 is 0, e to the 0 power is 1, so our slope is 6. So we can go ahead and write out our equation of a line tangent to this equation. So y minus our y value, which we found out was 8, equals our slope, 6, times x minus 0, or just x. So what we're going to be doing next is the derivative of function y is equal to k of t is given by dy over dt equaling 1/4 y plus 5. It is known that k of 3 is equal to 19, right? Write an equation of a line tangent to k when it's t is equal to 3. So same kind of thing. We have our derivative this time, and we know our point already, so I just need to plug in our value into our equation. So we know k of t is equal to y. We have the derivative of y, so we have the derivative of k of t, and we know that k of 3 equals 19, so when x is 3, y is equal to 19. So dy over dt evaluated when y is equal to 19. So we have 1/4 times 19 plus 5. 19 plus 5 is 24. And we are going to be dividing that by 4. So we get 6. So y minus 19 equals 6 times x minus 3. So equations of tangent lines, especially when we're really close to our value, gives us a really good approximation for things or functions where we can't really put a value in and get a good y value. So for instance, I can plug in 0 to our first equation that we had, f of x, 3e to the 2x. I can plug in 0 and it's not a big deal. I can figure out an exact value for that. But if I wanted to plug in 1, 3 times e to the second power is not super easy to figure out. Even if I wanted to do 0.5, it's going to be really hard to find this value without using a calculator. I can take this and I can use this equation of a tangent line to find the value that's pretty close to what our actual value is, but might be off a little bit. So for instance, if we look at this graph, f of 5 and our tangent line are going to be the same. But if I wanted to find f of 5.3, that's going to be about here, and that difference is pretty minute. Same if I go the other way around. So this is a good approximation for what we want. Okay, the function f and g are differentiable with selected values of f, g, f prime, and g prime given above. H of x is equal to f of g of x. Write the equation of a line tangent to h of x at x equals 4. So I need my point and I need my slope. So the first thing we're going to find is our point. So h of 4, which would be f of g of 4. So g of 4 would be 5. F of 5, if we look at our table, gives us -9. So our point is going to be 4, -9. Now we're going to take the derivative of h of x. So h prime of x is equal to f prime of g of x times g prime of x. And we're going to plug in 4. So h prime of 4 is equal to f prime of g of 4 times g prime of 4. Well, g of 4 we found out earlier was 5, so we're looking at f prime of 5 times g prime of 4. G prime of 4, it looks like it's -2. F prime of 5 looks like it's 3, so 3 times -2, which equals -6. They've used 6 for a lot of these. So our equation of our line tangent, y minus -9, so y plus 9 equals -6 times x minus 4. We're going to go ahead and, that's our answer. So now we're going to use that tangent line from part A to approximate 4.1. So what we're going to do is we're going to take our equation, y plus 9 equals -6 times our x value minus 4, and we're going to plug in 4.1 for our x value. So instead of x, we are going to have 4.1. So now we're just going to simplify this to the best that we can. So I'm going to go ahead and we have 4.1 minus 4, so we're looking at 0.1. -6 times 0.1 is -0.6. And if I subtract 9 from both sides, we get y is equal to -9.6. So even though I don't have 4.1 on my table, we know that it is a continuous function because they're differentiable. So I know that this value h of 4.1 is pretty close to what we have. Let y equal f of x be a function with dy over dx equaling 3x divided by y plus 4 squared, containing the point 1, -5. Write an equation of a line tangent to the graph, y equals f of x at 1, and use your equation to approximate f of 0.8. Okay. So one of the first things that I need to do is use the derivative to find my slope. They already gave us a point, so I'm going to go ahead and use this derivative to find my slope. So dy over dx, approximate it at the point 1, -5. So we have 3 times 1 divided by -5 plus 4 squared. So 3 divided by 1 squared, so our slope is 3. So we have y minus -5, so y plus 5 is equal to 3 times x minus 1. I'm going to move it over so y is by itself. This isn't necessarily needed, but we could also name it f of x, but we don't necessarily have to. So we're going to plug in 0.8 to our function. So y plus 5 is equal to 3 times 0.8 minus 1. We have this difference as -0.2. 3 times 2 is 6, so I know that this is going to be negative 0.6 again, and we're going to subtract 5 from both sides. So y is equal to negative 5.6. So f of 0.8 is about negative 5.6. And our last one here, on Thanksgiving, a delicious pumpkin pie is removed from an oven. There's a word missing. An oven whose temperature 175 degrees Fahrenheit. The temperature of the pie at time t minutes can be modeled by the function p, where dp over dt is equal to 1 over 50 times the quantity p minus 25. Use the tangent line to p at t equals 0 to approximate the temperature of the pie 4 minutes after being removed from the oven. So, we need to write the equation of a tangent line, so I need to find the slope and the point at 0 for t. The nice thing is our function has already given us a y value. So at t equals 0 is when we pull out the pie from the oven. So 0, 175 degrees is our point. Now, to find our slope, we're going to go ahead and plug everything into our dp over dt equation. One of the things that we know is that it's using p. P is that 175. So dp over dt is evaluated. This time we're going to say p of 0 is equal to 175. So we now know x and y. So I have negative 1 over 50 times 175 minus 25. 175 minus 25 is 150, so we have negative 150 divided by 50, so negative 3. So our equation of a tangent line would look like y minus 175 equals negative 3 times x minus 0, or just x. Now that we have this, we're going to go ahead and plug in 4. So y minus 175 is equal to negative 3 times 4. We get negative 12. And we're going to add 175 to both sides. So y is equal to 163. So the temperature approximately will be P of 4 is about 163 degrees Fahrenheit. So linear approximations are literally just finding the equation of a tangent line and plugging in a number that is close to that to get a better idea of what's going on either around it or to give a good approximation for something that we don't know. For things like ones we don't have equations for, or things in tables, that's kind of be the main thing that we use this for.